In this problem, we are given two sets, A and B, and a mapping between them two, right, from A to B. And given this, we're going to define a new mapping. This mapping is called PF, and it maps the set parts of A into the set parts of B. So maps subsets of A into subsets of B, right? The definition is this. The image of one such subset is just the set FC. In other words, the images of all the elements of C, right? And this is for any C in A. Okay, subset of A. Now, we have to prove that if F is injective or surjective, then so is PF. And then we have to check whether the converse are true, right? Okay, let's begin with the first, right? We're going to prove that if F is injective, then so is F. So is P of F. Right. Let's take two sets, C and D, which are subset of A, and such that PFC is equal to PFD, right? But otherwise they are arbitrary. So the only requirement is that the images through the function PF is the same, okay? Right. According to the definition of this, what this means is that FC, so the set of images of the set C, is equal to the set of images of the set D, right? And what this means is if X is in C, then there is Y in D such that Fx is equal to Fy, right? Because, well, this is what it's saying. All the images of the elements of C are also the images of the set of D. So for any point in C, there is another point in D, such that the two images are the same. But now we know that the function is injective, so this means X is equal to Y, which means that X is also an element of D. And since the argument is reversible, so this proves that C is contained in D, and since the argument is reversible, D is contained in C, which means D and C are the same set, and therefore the function P is also injective, right? Equality of the images implies equality of the arguments, right? Okay, now surjective. We're going to take a set D in B, right? Here, so a subset of B, okay? Now, F minus 1 of D is the set of all elements in A whose image belongs to D, right? This is the inverse image of D, right? All the points in A that map into the into the set D, right? Okay. Now, since F is surjective, every element in D is the image of some element in A. So if F is surjective, implies that any element Y in D is the image of some element of A. Right? Which means that F minus 1 of D is not empty. Okay, F minus 1 is D is not empty. So that means that there exists some set C in A whose image is precisely D, right? If this is not empty, well, there will be a set which is equal to this, and this set is, the image of this set is D, which means PF is surjective. Okay? For every set in B, there is a set in A whose image through PF is D, which means it's surjective. All right. So that proves the second, and now we're going to consider the converses. We're going to prove that that F injective implies PF injective. Right? We're going to prove that. Sorry, no, the other way around. We're going to prove that if PF is injective, then F is injective. That's what we want to prove. That's the converse of the first proposition, right? All right, we're going to take two elements, x and y, in A, so that x and y are different, okay? We need to prove that the two images through F are different too, okay? All right, if these two elements are different, then these two sets are different, of course, right? The two singletons are different sets, okay? Then PF of x is different from PF of y because we're assuming that this function is injective. So different sets map into different sets, okay? But what is PF? This is just f of x, right? And this is f of y. In other words, it's the set of all images of the points in this set. But there's only one point in this set, so there's only one image. So this set is actually this one. It's the set that contains the only image in this, the only possible image, right? And so is this one. This one is Fy. So what we're saying is that these two sets are different. So Fx is different than Fy. And the only possibility that these two sets are different is that the two elements that they contain are different. So Fx is different from Xy, and that implies that F is injective. All right? Okay. Let's see now, the second proposition is PF surjective implies F is also surjective, right? So for that, we're going to take y. Okay, we're going to take y in B arbitrary. So any point in B, right? Okay, then, of course, this set belongs to parts of B. Okay. And since PF is surjective, then there exists C, a subset of A, such that PFC is equal to Y. So in other words, the inverse image of this set is not empty, right? The inverse image of this set is not empty because of this, okay? Right. And we know that this set C cannot be the anti-set because the image of the anti-set is just the anti-set, right? So it's different from the anti-set. So this C is not empty, okay? Okay. Now we take x in C, and for any x in C, Fx is equal to Y, right? So in other words, for any Y in B arbitrary, we have found an x in A whose image is Y. So F is surjective. There you go.